Every time you open X, you see about 50 posts. But there are billions of posts on the platform, created by hundreds of millions of users. So how does the system decide which 50 to show you, in what order, in under a second? That is the problem this codebase solves. And the answer involves no handcrafted features at all. Just a transformer, your engagement history, and a carefully designed attention mask. Here is what we will cover. The For You feed is built from 4 components. Home Mixer, the orchestration layer written in Rust. Thunder, an in-memory store for posts from people you follow. Phoenix, the ML system that both discovers and ranks posts using JAX. And the Candidate Pipeline, a reusable framework that wires everything together. By the end, you will understand the full path from a feed request to a ranked list of posts, and why the architecture makes the trade-offs it does. Let us start with the big picture, before diving into each component. When a feed request arrives, Home Mixer orchestrates the entire flow. It is a gRPC server exposing a scored post-service endpoint. The pipeline runs in a fixed sequence. First, hydrate the query with user context like your engagement history and following list. Then fetch candidate posts from 2 sources in parallel. Hydrate those candidates with metadata. Filter out ineligible ones. Score the survivors with ML predictions. Select the top K. Run post-selection safety filters. And finally, return the ranked feed. This pipeline is built on the Candidate Pipeline Crate, which defines a trait-based framework. The core trait is Candidate Pipeline, and it is generic over a query type Q and a candidate type C. It expects you to provide implementations for each stage. Source for fetching candidates, hydrator for enriching them, filter for removing bad ones, scorer for ranking, and selector for picking the top K. Sources and hydrators run in parallel where possible. Filters run sequentially, because each one shrinks the candidate set for the next. And if any component fails, the pipeline logs the error and continues with what it has. This graceful degradation is critical for a system that must return results every time. Now that we see the pipeline structure, let us look at where the candidates actually come from. The first source is Thunder. Thunder is the in-network candidate source. It is a Rust service that consumes post-creation and deletion events from Kafka in real time and maintains an in-memory store of recent posts per user. When the pipeline needs in-network candidates, Thunder looks up the requesting user's following list, then fetches recent posts from those user stores. Because everything is in memory, these lookups take sub-millisecond time. No database round trips, no network hops to a remote store. The Thunder service impl exposes a gRPC endpoint called getInNetworkPosts. It receives a user ID and a following list, queries the post store for each followed user, and returns light post objects sorted by recency. It uses a semaphore to limit concurrent requests and prevent overload, and it tracks detailed metrics like post freshness, reply ratio, unique author count, and time range of return posts. The service also automatically trims posts older than a retention window, keeping the memory footprint bounded. Thunder handles posts from people you already follow, but the For You feed also surfaces content from accounts you have never seen before. That is where Phoenix Retrieval comes in. Phoenix Retrieval uses a 2-tower architecture to find relevant out-of-network posts from a global corpus of millions. The user tower takes your engagement history, passes it through the same Grok-based transformer used for ranking, and produces a single normalized user embedding. The candidate tower takes each post's hash embeddings concatenated with its author's embeddings and projects them through a 2-layer MLP with CLU activation down to a normalized candidate embedding. Both towers output L2 normalized vectors in the same embedding space. Retrieval then becomes a dot product similarity search. The user representation is a single vector of dimension D. The corpus is a matrix of n normalized candidate vectors. A single matrix multiply gives similarity scores for every candidate and JAX. LAX. Top K extracts the best matches. Because both sides are normalized, the dot product equals cosine similarity, which means the corpus embeddings can be pre-computed and stored in an approximate nearest neighbor index for fast lookup. This is the standard 2-tower pattern, but what makes it interesting here is that the user tower reuses the full transformer architecture, not a simpler encoder. Your engagement history is treated as a sequence that the transformer processes with causal attention before mean pooling into a single vector. Retrieval narrows millions of posts to hundreds, but the scores from dot product similarity are coarse. To produce the final ranking, every candidate goes through the Phoenix ranking model, and this is where the most important design decision in the system lies. The Phoenix ranking model is a Grok-based transformer that takes 3 groups of inputs concatenated into a single sequence: a user embedding at position 0, then a sequence of your recent engagement history, and then the candidate posts to score. Each position is built by projecting multiple hash embeddings through learned projection matrices. History positions additionally include action embeddings, encoding which actions you took on each past post, like whether you liked, replied, or muted it, and product surface embeddings indicating where you saw it. Here is the critical design choice: candidate isolation. During the transformer's attention computation, each candidate position can attend to the user embedding and the full engagement history, but candidates cannot attend to each other. The attention mask is constructed by the make-resize atten mask function in Grok. Pi. It starts with a causal mask, zeroes out the entire candidate-to-candidate block in the bottom right corner, then adds back only the diagonal so each candidate can self-attend. Think about what this means. The score for any given post depends only on your user context and that post's features. It does not depend on which other posts happen to be in the same batch. This makes scores consistent across different request batches and makes them cacheable. Without this mask, changing one candidate in the batch could shift every other candidate's score, which would make caching impossible and ranking unstable. After the transformer processes the full sequence, the model extracts just the output embeddings at candidate positions, applies RMS layer normalization, and projects them through an unembedding matrix to produce logits of shape batch by num candidates by num actions. These logits represent predicted probabilities for every possible engagement action on every candidate, like reply, repost, quote, click, profile click, video view, photo expand, share, dwell, follow author, not interested, block, mute, and report. The model predicts all of these simultaneously in a single forward pass. Having all these predicted probabilities is powerful, but they need to be combined into a single number to rank posts against each other. That is the job of the scoring pipeline. The scoring stage applies 4 scorers sequentially. First, the Phoenix scorer calls the Phoenix ranking model and attaches predicted engagement probabilities to each candidate. It builds a predictions map keyed by tweet ID, extracting action probabilities from logprobs via exponentiation. Next, the weighted scorer combines these predictions into a single relevant score. The formula is a weighted sum. Each predicted action probability is multiplied by a configured weight. Positive engagement actions like favorites, replies, reposts, and shares have positive weights. Negative signals like not interested, block, mute, and report have negative weights that push content down. Video quality views only count if the video exceeds a minimum duration threshold. The combined score then goes through an offset function that ensures even posts with some negative signal contribution still get a non-negative base score, preventing the feed from being too conservative. Then the author diversity scorer ensures the feed is not dominated by a single prolific author. It sorts candidates by weighted score, then for each author, the second post from the same author gets its score multiplied by a decay factor, the third by the decay factor squared, and so on, with a floor to prevent complete suppression. This is a simple but effective mechanism. It does not remove posts, it just attenuates repeated author scores so that diverse content naturally floats up during selection. Finally, the OON scorer adjusts scores for out-of-network content, and the selector picks the top K. Before these scored posts reach your screen, they pass through one more gauntlet of filters. Let us look at how the system ensures quality and safety. The pipeline applies filters at 2 stages: pre-scoring and post-selection. Pre-scoring filters are about eligibility. Drop duplicates filter removes duplicate post ID. Age filter drops posts older than a threshold. Self-tweet filter removes your own posts. Retweet deduplication filter deduplicates reposts of the same content. Previously seen posts filter and previously served posts filter prevent showing content you have already seen. Muted keyword filter and author social graph filter enforce your block and mute preferences. These all run before the expensive ML scoring step, which saves computation. Post-selection filters run after scoring and selection. The VF filter checks for deleted, spam, violent, or otherwise prohibited content using a visibility filtering service. Dedupe conversation filter collapses multiple branches of the same conversation thread. These run after selection because they require additional hydration data that would be too expensive to fetch for all candidates, so the system only checks the final selected set. Let us step back and see the full picture. A feed request arrives. Home Mixer hydrates it with your engagement history. Thunder and Phoenix retrieval fetch in network and out-of-network candidates in parallel. The candidates get enriched with metadata, then filtered for eligibility. The Phoenix ranking transformer scores each candidate independently, predicting 15+ engagement probabilities. The weighted scorer combines those into a single relevant score. Author diversity dampening ensures variety. The top K are selected, safety checked, and returned. The entire architecture is built so that the transformer does all the heavy lifting. No handcrafted relevance features, no manually tuned heuristics for content matching. Now that we understand what the system does, let us talk about why it was built this way. The single boldest design decision here is eliminating all hand-engineered features. Traditional recommendation systems have massive feature engineering pipelines, content similarity features, social graph features, engagement history aggregations, time decay functions. Each one requires its own data pipeline, its own serving infrastructure, and its own maintenance burden. By giving the transformer raw engagement sequences and hash embeddings, this system pushes all that complexity into the model. The model learns which patterns in your history predict which actions on a new post. The trade-off is clear. You need a much more powerful model, but you get a much simpler serving stack. Candidate isolation is the second critical decision. Without it, you would need to score all candidates together as a set, and the score for any post would change depending on what else is in the batch. That breaks caching, complicates a /B testing, and makes the system harder to debug. With candidate isolation, each post gets a deterministic score based only on the user context. You can cache scores, reuse them across requests, and reason about why a specific post ranked where it did. The cost is that the model cannot do cross-candidate reasoning, like learning to promote a post that provides context for another post in the same feed. But in practice, the consistency and cacheability benefits far outweigh that limitation. What we have seen is a recommendation system that bets heavily on the transformer. It replaces feature engineering with raw engagement sequences. It uses a novel attention mask for independent candidate scoring. It combines a two-tower retrieval system with a full transformer ranker. And it wraps everything in a composable Rust pipeline framework where adding a new filter or scorer is just implementing a trait. The next time you scroll your For You feed, you will know exactly what is happening behind the scenes. Your engagement history flowing through a transformer, predicted action probabilities being weighted and combined, and author diversity dampening, ensuring you see more than one voice. That is the X recommendation algorithm.